in. So no major announcements for Soda, except Ming will be taking over as co-chair, kind of in my spot. I think I'm formally stepping down as co-chair, but I'll be around to volunteer, and there's a lot of things to help with. So this will probably be the last one that I formally present, although I'll be available to help host future Soda meetups. Um, yeah, so welcome to our February Soda meetup. We have two great talks today. The first will be by Dr. Mihir Mongia at Meta, and then Dr. Mingxun Wang, goes by Ming, at UC Riverside. Just for the meeting, like our etiquette, please remain muted during the entire presentation. If you unmute yourself during a talk, one of us will mute you just because we'll assume it was an accident, and we'll take questions after the presentation. Each presentation should be about 20 to 25 minutes, leaving enough time for about 3 or 4 questions. If we run over that time, we can, if everyone consents, we can stay afterwards and have more questions, or we can just send contact information afterwards and everyone can connect with the speakers later on. To ask a question, just either, depending on how many people are here, just click raise hand, or if there's fewer than 30 people, you can just speak up. The chat questions also, feel free to post those at any time. We'll answer those at the end of each talk. And whenever you ask a question, go ahead and turn on your video just so we can kind of see who's talking. And we'll also be posting these presentations on the SOTA website, along with the backlog of 3 other ones that we haven't posted yet, but we have volunteers that are helping out now. So also, if you'd like to volunteer or join us or anything, just give us an email or scan these QR codes, and there's links on the website to contact us. With that, I guess we'll go ahead and get started. Dr. Mihir, are you ready?
Oh yeah. Okay, let me see if I can share my screen. It says I cannot share my screen while other participants are also sharing.
All right. Okay. Oh, wait, shoot. Sorry. I stopped. Okay, here we go. These are parts of the videos we'll edit out. And when we post a video, we'll edit out questions too. So if anyone's shy, don't worry, we won't put you on YouTube.
Awesome.
Cool.
Can you guys
All
see
right.
a PowerPoint slide that's full screen right now?
Yep. Take it
Awesome.
away.
So I'll get started. Hi everyone. So my name is Mihir, and I'm going to talk about some work I did with my advisor while I was a grad student, Professor Hossein Mohammadi. This work was done at CMU or Carnegie Mellon. Professor Mohammadi has now moved to UCLA to much warmer pastures. I did a postdoc with Mike Snyder for a year. That's how I met UA, and well, now I work in Meta as just an employee. And I'm going to talk about a specific piece of work that we published in Nature Biotech last year in January. It's entitled Fast Mass Spectrometry Search and Clustering of Untargeted Metabolomics Data. It's basically roughly, we develop a bunch of fast routines for processing tandem mass spectrometry. Of special note, I want to note is the second speaker today is also on this paper. So Ming and Peter Dorstein kind of made the, I guess I would say, foundational computational routines related to Mass Spec, and I've just been lucky enough to build upon them and maybe make them a little bit faster. So let me proceed. So I'm going to say something that you guys know better than I do, honestly. Just roughly going to talk about tandem mass spec, right? So, you have a solution sometimes, and in the solution, you have some molecules which you yourself cannot see. What a tandem mass spectrometer will often do is separate the solution into different mass bins. So 0 to 1 Dalton, 1 to 2, 3 to 4, and so on. And so in this cartoon figure, you might have a mass region from 95 to 96, a mass region from 211 to 212, and 423 to 424. And then each of these mass bins goes through another fragmentation step. Basically, the kind of molecules in that mass bin are smashed with an electron beam. The fragments are accelerated through a tunnel. And in the tunnel, there's this thing that stretches things, it's a magnet. It basically stretches the fragments based on their mass to charge ratio. So basically, the end, you kind of get this graph, right? And basically, the x-axis is mass to charge ratios, and the y-axis is basically how much of each fragment basically exists. So The signal is sometimes a bit more noisy, just to give you kind of a picture of what's going on. And at the end of the day, basically you put a solution in through a mass spectrometer, you get a bunch of graphs. And each graph is associated with a number, which we'll call the precursor mass. Cool. So what people colloquially say, right, is that tandem mass spectrometry gives you fingerprints that are present, or give you fingerprints of each molecule present in your sample. Okay, and so I think it's really maybe it's good to internalize what this really means, right? So maybe a good way to internalize it is think about what would the FBI do with fingerprints? So let's suppose you have a crime and you find a fingerprint. What the FBI will do is go search the fingerprint against a database. If they find a match, they kind of all of a sudden know who the criminal is, or at least they know some information about the criminal. Maybe they don't have the identity, but they have maybe past crimes or something else. Number two, right? If you have two crimes with the same criminal, then you know that with the same fingerprint, then you know there was only one criminal that was common to these both crimes, which can be important. And the way that can be important is that the crimes may be related, right? So let's suppose in one crime scene, someone stole a bunch of digital data from a hard drive. In another crime, there was a kind of a, let's say, a picture or a canvas stolen. Well, then you may begin to hypothesize maybe inside the canvas itself, there's a bunch of binary data encoded, and your job is to maybe figure out what that data could have corresponded to. That'd be something you see on Law and Order or some other TV show, for example. Now, so we have this picture in our mind, right? Fingerprints can be useful and something that we all kind of know. Well, basically, we have analogs to this in the mass spectrometry world. And let me kind of explain a few examples that I've seen. I would love to know a lot more. I think you guys probably know much more than I do. So at UC San Diego, I think Ming and Peter Dorstein have cultivated this repository called GNPS. And here people have basically, or scientists around the world, have deposited their data. And essentially, you can click on any of these links, and scientists also annotated metadata about their data, right? So, for example, you may find that a certain experiment was done in females, infants less than 2 years old, and people collected their feces. Okay. And okay, so why could this be useful, right? So just like the FBI, we created this database, and then this routine called Mass that was developed by Bing in the past. What it basically allows you to do is discover some cool science. So let's suppose you have a toxin or a fungicide, and you know the mass spec for it. And as a public health official, you have this question: is this toxin occurring near humans? What you can do is you can search the spectrum against this huge database, which at least historically, maybe 2 years ago, had a billion mass spectra. If you find a match, you can look at the metadata. If the metadata, for example, says infants, then you all of a sudden have this really important information saying, okay, this toxin occurs near infants, which is super critical for any country to know. The other cool thing you can probably do with this, or I've seen this happen, is you can find important information in analog studies. So specifically, there were some scientists studying non-alcoholic fatty liver disease in humans, and they found that a specific molecule, or rather a specific spectrum, was appearing often in NAFLD. They searched the spectrum on using MAST, and they found a match to a study where they induced rats with NAFLD. In the rat study, they found that basically if they treated the rats that had NAFLD with an antibiotic, that spectrum essentially disappeared. So this began to lead to the hypothesis that the spectrum that you see in humans is actually caused by a bacteria. And using some other routines that are hosted on GNPS, they were able to kind of almost isolate the structure of the molecule as well. Another application could be like, can we find analogs of cancer-fighting drugs? So let's suppose you have a molecule that turns out to kill cancer, but it's also still toxic to humans or the host. It's often the case that derivatives, or that molecule minus or plus a few atoms, can be more benign. And so what you can do is you can try to find naturally existing derivatives using MAST. And if you find them, you can figure out where they're located and go retrieve them. They may be in the middle of the ocean, but at least you know they exist and you can go find them on your own if you care to. Some other examples, on the left, I was giving a talk at ASMS once, and I talked to someone from 3M, and they don't really work on biology stuff, but basically he sent me a LinkedIn message at some point saying they really care about huge databases of Tandem Mass Spec or some other type of Mass Spec, and he was curious how can you search them quickly. So that's maybe not in our wheelhouse, but seems to be important at least in some other domains. And then Mass Spec imaging. So in Mass Spec imaging, what happens is you'll take like a tissue slice, put it on a slide, and every micrometer or every microcentimeter, depending on what resolution you care about, you shoot the tissue with a beam. And at the end, you'll get a kind of spectrum. And what's cool about this is the spectrum is really kind of sensitive to what type of tissue you're looking at. If it's cancerous tissue, you'll get a different spectrum or different peaks. If it's fatty or liver or something else, you'll get different peaks. And so this kind of spectrum can be really useful for just classifying what parts of the tissue are cancerous or kind of what other things you care about. Okay, cool. So we have these three applications, and there's many more probably. What's common among all these applications is the compute is huge. So when we ran experiments at some point, we use one CPU to compare one query against 1 billion spectra inside GMPS. It took 5 days. Mass spec imaging is known to generate almost terabytes of data every 2 or 3 hours. The throughput will just double every 2 years from now on, right? And 3M wasn't specific with their needs, but they basically just stored, years or decades worth of data, and they want to see how to basically investigate it. Now, what's also true in all these cases that I've talked about, there's a common routine or a common computational procedure. Basically, you have a set of spectra in a database or a data set, and you have a query spectra, and you really just want to see how close is that query spectrum to all of the spectra in your data set. And you care about figuring out what is the closest spectrum. Now, the natural question is, how do you measure closeness? So there's two metrics that are kind of commonly used, and probably in the future there'll be some other metrics that are more complicated and represent other types of kind of, let's say, biology or kind of modifications in the chemical space. I only talk about part A for the kind of lack of time. In part A, suppose you have two spectrum with the same precursor mass. All you're going to do is look for peaks in the same location among the two spectra. And if they're in the same location, you're going to multiply the values and add them up. So in this case, in part A, we have 6.2 and 3.2 lined up, and 10.2 and 16.3 also lined up. And we'll just multiply the values and add them up and get a value. Now, in reality, we would normalize the score to get between 0 and 1. For now, I won't talk about that. That will just hide the main message of the talk. Cool. So traditional mass search, this is a seminal routine developed by Ming and Peter Dorstein. So what's happening is something like this, right? You have a query peak, you have a query, right? And every peak in that query, you're going to go see inside spectrum 1 if that exists. If it does exist, you'll contribute these multiplied values. If not, you'll essentially contribute 0. So here we have 10.3, 9.8. Multiply the two values. In the second peak in the query, right, it doesn't exist on spectrum 1. So essentially you're multiplying by 0. And so on. Now you do this for every spectra. And so essentially you're doing basically, you can think of it as 16 pieces of work, right? There's 4 peaks in the query. Each time you look inside a spectra, and there's 4 spectra. So you have kind of 16 pieces of work. Now, note that this computation is probably similar to something you've seen maybe in linear algebra in the past, that it's just kind of just like multiplying matrix times a vector. So, this matrix, each row is basically red or blue, depending on the spectra. So spectra 1 is red, spectra 2 is blue, and so on. The vector corresponds to the query. And so this computation I did above on this last slide is literally just like this thing on the right. Now, also something probably, maybe you don't know off the top of your head, but it's also the case, is that matrix vector multiplications can be viewed in many ways. One way is to view it as just scaling columns of the matrix by values in the vector. So for example, in this case, right, this 4x6 matrix, you take the first column, scale it by 10.3, 10.3 being the first entry in the vector of the query. Take the second column, scale it by the second entry in the vector. Take the third column, scale it by the third entry in the vector, and so on. And so when you think about matrix vector multiplications this way, what ends up happening is you can redo the operations of MAST. So you can take the first query peak, and instead of going on to the next query peak, you can, for that single query peak, look at all the spectra. So it would look like this, right? Query peak was to spectra 1, then next to spectra 2, then to spectra 3, and then to spectra 4. And you just keep doing this. So we did this, but still there was 16 pieces of work. This can be improved in the following way. You can create lists of non-zero entries. So what does that mean? What we can do is for position 100.0, we create a list of our database, and we only put the spectra that have non-zero peaks. So in 100.0, there's 3 entries. It's missing an entry for spectra 2 because spectra 2 has nothing in that first column or at position 100.0. On the other hand, in location 200.0, there is a list with only 1 entry, and that list contains spectra 2 only because spectra 1, spectra 3, and spectra 4 do not contain anything for that location. Okay, so let's suppose we do this. Then what happens is our computational routines become a lot faster. So let's take a query peak, right? And let's retrieve that list for position 100.0. We can see that at the bottom. And we just iterate through the list. So we'll go to spectra 1, then spectra 3, and then spectra 4. Note we skipped spectra 2 because, well, it wasn't in the list. Then we can go to the second entry of the query, retrieve that list for 200.0, iterate through that list only, and you see we've done no work for spectra 1, spectra 3, or spectra 4. And we can just proceed this way. So now you can see the screen is more blank, right? So there's less work done. What's also true in the kind of world of mass spectrometry is that, like, at least in high resolution mass spectrometry, for any peak location, really maybe 100th or 1000th of the spectra in your data set will have a peak in that location. So you can imagine in a real world scenario, this figure would be very, very white, and thus you'd have a lot less work. So just some benchmarks that we put on our paper. So, MAST was the first work done in this area, and, established these computational routines for analog search and just exact search, and that's in red. And for Mass Plus, we're 2 tick marks below, and that's regardless of the data set size. And so we're maybe 100x faster. I think probably if we did better software engineering, we can make it even faster. So that's there. And that's kind of, okay, so that's kind of this idea of searching one spectrum against a billion. There's another important routine in the area of mass spectrometry called molecular networking. And let me motivate that kind of with the application. So what happens in molecular networking is you have a bunch of spectra. And let's suppose in the example, we have 3 precursor masses, and for each precursor mass, you have a bunch of spectra. What you're going to do is you're going to cluster within each precursor mass first, and then you're going to compare all the clusters regardless of the precursor mass. So in this specific case, right, we may have 2 clusters for 1240.8. That's why you have 2 nodes. You have 1 cluster for 1224.83 and 1 for 950. Once you have those clusters, you're going to do sometimes what we call an error tolerant search or error tolerant comparison between the clusters. And I won't explain that right now just because of lack of time. And once you do that, you'll attach clusters that have a high score under the error tolerance score. And you put a weight on the edge that corresponds to the weight difference between the 2 clusters. And why is this useful? Is because I guess a lot of people would know better than me, honestly, is that certain weights, right, correspond to basically a certain combination of atoms, and that can be really useful. So let me give you some more maybe why is this biologically useful. There's a paper published maybe in Nature Chemical Biology maybe 2 or 3 years ago, and they wanted to see kind of the molecular differences between germ-free mice and SPF mice. So they created a molecular network initially. So on the left, you have some blue nodes which correspond to SPF mice, and you have red nodes that correspond to germ-free mice, and one that has kind of like the large one that basically occurs in both germ-free mice and SPF mice. Initially, we didn't know, or they didn't know, what all clusters the molecules corresponded to. They, however, knew a few hits. So the things current in yellow, they knew the actual molecular structure of those. Now, because of these kind of weights on these edges, they could kind of hypothesize which molecules would be added or subtracted, or which atoms would be subtracted or added from the molecule that's in yellow to get the structure of the things that don't have basically a yellow border. And so that way, they could annotate more of the molecules that are present or absent in germ-free mice versus SPF mice. You can imagine in a kind of an ideal case, in a much larger network, right? You have a huge network. Initially, you just have a few hits to which you know the molecular structure. But the edges, the kind of immediate edges of the molecule or the molecules for which you know the structure, you can hypothesize the adjacent molecules or the adjacent clusters, adjacent nodes. And then you have a new set of hits for which you know the molecular structure, and you can extend beyond them. And so just with a few hits, potentially, you can annotate a whole new network. So that's kind of cool, and that's biologically important. We developed routines in this area as well. So there was basically someone named Ari Frank who developed this very, very fast clustering tool called MS Clustering. It was published in Nature Biotech maybe 7, 8 years ago, I believe. And so that's in the blue in part A. And we developed Clustering Plus, which is just an improved version of MS Clustering. And for basically small data set sizes, maybe 100,000 or a million, or 10x faster. As you get to larger data set sizes, our kind of gains are much more significant. And we only plotted basically things that finish in under 24 hours. So you can see that for basically 10 million, MS clustering finishes in 24 hours, but it does not finish for 100 million, whereas our tool does. There's something called spectral networking, which is the second part of molecular networking. And you can see, and I think this was done by Nuno Bandeira at some point. I'm forgetting the exact author, so forgive me, but someone at UC San Diego. And you can see that basically our routine is quite fast compared to this. So even for 10 to the power of 5 or 100,000 spectra, we're almost 3 tick marks below. And we can go up to a million and finish in less than 24 hours. And this is kind of cool because what's happening in spectral networking is you're comparing every spectra to every spectra. So in the case of 10 to the 6 spectra, you're actually doing 10 to the power of 12 comparisons, and we can still finish in less than 24 hours. So it's quite cool. Part C, we're basically we're appending these two routines together, and we call it molecular networking. And so we're getting kind of also significant gains here, as you'd expect from looking at parts A and part B. Okay, so in conclusion, right? So tandem mass spectra, they produce fingerprints, and they're really useful for getting scientific knowledge, things you would care about as a biologist. These all require a lot of compute, though. Okay, and what's happening, as everyone will probably agree, is that the number of mass spec you're getting out there is just going to double, quadruple over the next 5 to 10 years. And so just having better routines is super critical, just to kind of have a functioning kind of way of life and kind of when you're doing these studies. We made the routines probably 100 to 1,000x faster. We could probably make them even faster if we did better software engineering. Kind of right now, the main things are algorithmic improvements. And yeah, so that's it. I do believe that, right? So, mass spec imaging isn't all MS2. Mass spec imaging is mostly MS1. So I believe that, kind of these algorithms are quite general in the sense that they can apply to all types of mass spec. And so in that sense, maybe the work is maybe more impactful. But I have a feeling that people in this community know more than I do. And so at some point, I would love to discuss with people. But I think for now, It's on to Ming.
Great, thank you. Thank you, Mihir. All right, up next, Ming, if you'd like to share your screen and discuss MassQL, a SQL-like language for querying mass spec databases.
Yeah, thank you, thank you. And I will admit, I love going second after after Mihir introduces a lot of the concepts, so I don't have to spend time on that. So thank you so much, Mihir. I think a lot of you have heard me talk about this, so feel free to tune out. But this is something that I'm excited about, and we're always excited about the tools we create. But I think one of the things that I want to throw out there is we created this, and I'll tell a story about it, but because I'm lazy, fundamentally I'm pretty lazy, and you make tools for people and you make tools for yourself, and it's a nice time whenever both of those intersect. So I think that's what I like to do. So thanks, Daniel and you for having me. But we'll get started talking about MassQL and kind of how it all started and what I think it can do. Just very first, here are my disclosures. And so one of the things that Mihir also alluded to is this: we have a lot of data out there now. This is in difference from about 10 years ago, where there was just very little data that we could actually work with. And so it really didn't really motivate why we wanted to develop algorithms and tools to kind of leverage this data. And so throughout the last 10 years, we can see this, this pretty steep growth from several of the big metabolomics data repositories. So Metabolites in the UK, Metabolomics Workbench, and Massive here on the US side. And then there's also things coming up in Asia that are contributing to this growth as well. And so just to give you a sense here, the number of raw files, we're well over 1 million these days. And that's a lot of data to play with, and we want to think about ways to mine it. And as Mihir pointed out, one of the questions that you can naturally ask is, given this tandem mass spectra, which is a fingerprint for a particular molecule, where in all this public data has this occurred before, right? So this is kind of an exact match or near exact match kind of query that we could do, and that's super useful. As Mihir pointed out, and it's ripe for, and they've also seen the algorithmic innovations. Now, I want to just point out another type of question that especially chemists will want to ask. And so, okay, so and also here, what we want to cast this problem as a nice visual is in this gray circle, gray oval, we can think about all the diversity of all the metabolites that we can capture by mass spectrometry. And again, we're talking about 1 billion to 2 billion tandem mass spec as a proxy for how much we're actually measuring. So that's an underestimate, but we're talking about in this billions plus category. And the amount of known metabolites is rather small, maybe 5 to 15% that we can putatively annotate. And there's other islands of novel chemistry and novel metabolites that have novel activity that we might be interested in. For example, there may be some sort of antibiotics that are aminoglycosides, or there may be siderophores that are binding small molecules that are implicated in the microbiome, or there may be new metabolites of drugs that we may see, or alternatively, there may be other classes of environmental pollutants that we're missing that's already obvious in the data, but we're just not actually being able to pinpoint saying this data represents that class of pollutant. So there's these natural kinds of islands of chemistry that we can start identifying, grouping up, and prioritizing. Now, a story that I want to tell here is a couple years ago, near the waning years of my postdoc, I was working in Peter's lab. And one of the nice things about my collaboration and our working relationship with Peter is a mass spectrometrist by training, and I'm a computer scientist. And so we see things differently, but I think in a complementary way. And one of the natural questions that Peter had asked and kind of posed was, hey, we have all this data, right? And we had already published mass at that point. And he was asking, hey, we can ask if we've seen the same molecule before, but given all this public data, can we cast a slightly bigger question and say, can we find all the carnitine molecules that are out there? Now, I know a little bit about chemistry. I can think that, I know what carnitines are as a particular functional group that is very distinctive. And I also know that certain types of compositions in small molecules or certain types of structures that are conserved imprint distinctive patterns upon the mass spectrometry data. This is the kind of, we take this for granted, especially for the mass spectrometrists in the room. And so just as an example here on the far left-hand side, if there's an iron that's bound in this particular small molecule, it has a very distinctive isotopic pattern in MS1. Same thing for bromine. Now, if we go to the right-hand side, we can see distinctive fragmentation in the tandem mass spec for certain substructures in the 2D structure. Now, for carnitines, I know a little bit that it may have, for certain classes of carnitines, maybe it's like a 59 Dalton neutral loss and an 85 Dalton actual MSMSP. Armed with this sort of information, I also know how to engineer software, build software at my whim, right? And so we can build a bespoke piece of software that can look for exactly that pattern that I use my brain to kind of figure out. And then we can start scaling this out, building a custom system to really search through all this public data and arrive at an answer that says, hey, putatively, we think these tandem mass spectra, given this sort of conserved pattern, they may be carnitines, and we can start diving deeper into it. Now, the problem is that once you give people this power, right, and once they have a taste of this, they'll want to ask more questions. Right? There's a saying in English, in American English at least, if you give a mouse a cookie, he'll want a glass of milk. So you give them something small and they'll want more. And the problem is they might ask for brominated compounds, siderophores, saccharides, peptidic natural products, the list goes on. One of the things is there's no way that I want to entertain that particular request and actually serve, build a custom solution for every request that comes through. That's not sustainable and that's not particularly fun, right? But what is fun for a computer scientist is thinking about, can we think about something that's a little bit more universal, right? And can we empower chemists to do this themselves without me actually having to do anything, right? So this is this whole idea of automation, but also giving power to chemists that do not have a very extensive computational expertise. So let's see if we can think about a solution for that. And so we came up with a new tool called the Mass Spec Query Language, or MassQL for short. And so just to highlight what we want to think about here is we want it to be first understandable. We want it to be a reasonably natural language that's meant for mass spectrometrists that within 5 minutes, they'll feel that it's natural and they can read and write it. As opposed to requiring them to learn tons of Python and all these data formats and all this stuff. Number two, it should be flexible. It should be able to think about it should be able to capture the myriad of different patterns that they want to express, not only in mass spectrometry, but in mass spectrometry adjacent dimensions such as retention time and mobility. Third, it should be reasonably scalable. It doesn't really help us if it can only search through 5 spectra whenever you have 1 million spectra laying in 1,000 LCMS files that just came out the mass spec over the last week. And then finally, it should be reusable. If we create a language that people spend this time to codify a particular pattern that they want to find, we want it to be in such a way that it can be used as a medium, MassQL can be used as a medium of communication to others within the lab and throughout the field. So this is a way to unambiguously express some sort of pattern other than in kind of written English, right? And so those are kind of the pillars that we thought about when we created MassQL. And it was, I was thinking back on it just because the paper was finally accepted in principle a few months ago. And so we'll see when it comes out. But it started just as a small conversation. I still have the text messages with one of my friends saying, what if we did this? What if we did that? Would this be confusing? Would this make sense? And so it was a long journey to arrive at a consensus sort of language and grammar. But I just want to give you a taste of what it may look like. And so first, again, this is a subset of the things that you can do, but I just want to, it's a language, so I want to show you what you could be speaking here. And so in the top left corner, one of the most natural things is looking for specific masses in a spectrum, whether MS1 or MS2. So we can express that. In the top right-hand side, we can think about losses from precursor. So again, you can say, I want to look for a spectra that has a loss from precursor. This is particularly important in the MS2, not particularly MS1. In the bottom left-hand corner, we can start expressing gaps between any two spectra within, or any two peaks in a spectrum. And on the bottom right-hand side, we give the power to say, hey, there's some relative intensities between different peaks, and you can start expressing that. Again, these are primitives. These are kind of the most basic building blocks that you can use in MassQL, and this is still a subset of them. But one of the powers of this is start composing multiple of these criteria together into something more complex and expressive. Now, one of the things is it may seem not super fun to learn a new language, but one of the things that we try to do recently is to make it even more accessible here. And so a lot of us are probably familiar with this, but large language models have become significantly more powerful in the last couple of years. So these days, we taught one of the GPT models to understand MassQL, and so you can interact with it as a chatbot and say, write me a MassQL query in English that does X, Y, and Z, and then it'll write you something here. So that's something you can definitely interact with. And just to highlight a really quick example from a collaborator at UC Riverside, Daniel Petrus, he's interested in this class, or was interested in this class of natural products called albicidins. And so he knew in his mind that this particular class of compound produced unique fragmentation at 468 and 660 m/z. Again, not the most complicated thing. He wrote it in just a few minutes. And so what he was able to do was he had published a paper back in 2017 discovering a whole family of these albicidin-like molecules. And so what we could do very, very quickly is to recapitulate those findings to find exactly what he had published on back in 2017. But because we also had the raw data, the MassQL query that he could leverage against this data, what we tried to do was cast the question here, what else did we leave on the table? Because MassQL is comprehensive to the particular pattern that he's looking for, in blue here, we have all the molecules that he had identified in his original paper. But in gray, we also found putative albicidin-like molecules that were missed in his original publication, just because he was not thorough in his exploration. Now, casting this problem within MassQL, you could cast a comprehensive net to find what he actually wanted to find and have more putative analogs than he had originally published on. So as a way to expand your own efforts, instead of looking at spectra one by one, this can be a useful pre-filtration tool to really scale up your manual kind of inspection efforts. And this third point that I want to highlight here is this idea that we can start scaling this approach up to cast these queries against larger and larger volumes of data. And so this was a paper that we published back in it's 2024. So I guess it's not that long ago. But one of the things that we wanted to look for, and following up from what Mihir pointed out in his presentation, we had a paper in 2020 looking at some novel bile acids. And so we had discovered a family of conjugated bile acids that are being produced by the microbiome in our gut. And so we wanted to ask the question here, what is the full diversity of these conjugated bile acids across all of this data? So we can really have a catalog and think about what is the chemical diversity that we should even think about, even if we don't have the full chemical structure for everything. And so Ipsita Mohanty was the first author here. And so she has an understanding of the fragmentation of bile acids. And so just show one example up here. And so there's two very specific fragments that she was able to craft a query and start searching for it. So this happens to be 319 and 337. So this is crafted out of the domain knowledge in her brain. And so once we have this query, we can start thinking about applying this to all of the public data that we have. And so we actually started off by taking this query and searching it across all of the Orbitrap data that's publicly available. And so this is about 100 million MSMS spectra that we searched, and applying, and this was first searching specifically for this trihydroxyl bile acids. We found about 270,000 MSMS spectra that had this particular signature. And then we did other things to make even this 270,000 a little bit more tractable. We clustered for identical MSMS spectra to reduce that redundancy, and we organized it into families of related fragmentation that we call molecular network, and we started visualizing that particular diversity. Now, the net result of this, about being able to cast a much larger net and thinking about the chemicals that come out, we first started off, before we had done this work, there are about 97 known bile acid modifications in the literature. But after this, because we cast this large net, looking at the actual data out there using this MassQL query, there were about thousands of MSMS evidence for modifications of these bile acids. So it's a pretty large growth, but using a data-driven approach. Now, this is just the start for this particular work, right? Now we can identify the MSMS signals. We've solved some of the structures in that particular manuscript, but there's no way that we can confirm it for thousands, right? Getting standards and validating the MSMS and the hypotheses developed here. But MassQL at least gives us a vehicle to develop these hypotheses in a data-driven way when you're staring at these millions of LCMS runs, and potentially, not exactly in this case, but you get hundreds of millions of billions of tandem mass spectra to start sorting through. So because we had MassQL to bear on this particular problem, it became, we were able to end up at this result that we can now carry forward in subsequent projects and publications. Now, important for this particular audience is, if you want to start using MassQL, we want to make it as open as possible. So right now, we have a Python API that you can integrate into your own software. We have an R API that you can integrate into your own software or bioinformatics pipelines. And this is all open for free-for-all academics and industry. So we license it prolifically with the MIT license. But additionally, for people that are in metabolomics that are not particularly software developers, we've also integrated it into many of the open source tools out there, such as, obviously GMPS and all that platform stuff, but also OpenMS, MSDial, MZMI, and other tools such as Metaboscape for the commercial side. So that if you can learn MassQL once, or you take a MassQL query and analyze your own data in whatever software you prefer, you can hand it off to somebody else and reproduce that result in another piece of software. So the whole goal here is that we want it to be an actual language that's universal. It doesn't really help us if only one piece of software speaks it. So that's kind of some of the stuff that we've put together and corralled the community to start supporting, this language that can be used, across a lot of the open source and commercial software. And then finally, at the end of the day, kind of circling back about MassQL here is, can we come up with a universal computational solution? We think we did. Now, whether by your definition of universal, it might not meet those particular criteria, but in the sense of being able to express many different types of queries for many different applications. In our publication, we have like 35 different applications across different types of fields. These are little vignettes on how MassQL can be useful, not just in microbiome research, but in terms of environmental chemistry, metabolomics, natural product discovery, just to name a few, right? And so we think that gives us evidence that it's useful by a large swath of the community, even though they don't want to share, there might be not applicable, MassQL queries are not applicable across those fields, but it demonstrates that this particular type of analysis is pretty universal across everybody who does mass spectrometry. And so finally, I just want to say, this work couldn't have been done without all the collaborators that actually gave us feedback in telling us what was good, what was bad, and what was needed in MassQL, as well as we are very fortunate that many of our collaborators even take a chance to use our crazy new ideas and crazy new tools. So I've been very fortunate during my career to have such supportive colleagues and mentors throughout the field, as well as the funding. We couldn't do anything without the funding from NIH, DOE, and private funders out there. So I'm happy to take any questions, and thank you guys so much.
If not, I'd like to thank our speakers again, Ming and Mihir. Yeah, 2 great talks today. Also, yeah, our next SOTA meetup's in 2 months. Not sure who will be hosting it. It might be Ming, might be Yue, might be myself again. We'll see.
Well, I'll say, because I'm taking over as co-chair, I will be hosting it. I'm done teaching, so you got plenty. It'll be good. It'll be good. So, well, Yue will be here too, so we'll both be here. But I'll be hosting it, and we'll find some great speakers too. So.
All right, we'll have a new host, and yeah, if anyone has any ideas for any presentations, Yue posted the link at the top for if you'd like to sign up to give a talk, or if you'd like to nominate someone else, if you have a suggestion for that or a workshop, or if you have any software you'd like to list with us on our curated software list, which Nextflow for MS is the next thing to put up there. So yeah, just go ahead and fill out those links. And thank you, Ming. Thank you, Mihir. And I'll be seeing you all around. Great day.